Uh, so we're still in chapter 20 in Dr. Balmester's Physics 2 class, studying the second law of thermodynamics, of which there are several forms. For two, there are the refrigerator and the engine statements of the second law that we've already talked about like last week. Recall that the heat engine statement is that no cyclic process can convert heat completely into work, which in terms of the efficiency, this is the efficiency for a heat engine. 1 minus, well, actually, first form let's look at is in terms of the work done by the engine, and this is divided by the heat from the high temperature reservoir heat that comes in. Well, this then we can give in terms of just the heat from the high temperature reservoir that comes in, and this is the heat ejected. I have it in the wrong order. Yes, this must certainly be less than 1. And so we can state the second law would be stated. The efficiency then has to be less than 1. So that segment would be that QC, the heat ejected, discarded at the lower temperature, is not equal to 0. Anyway, it turns out that there is a maximum efficiency for a heat engine running between 2 temperatures. That's the efficiency of a special cycle of O whose processes are reversible. That's the so-called Carnot cycle. In that case, the efficiency the maximum efficiency is the ratio 1 minus the ratio of the temperatures in Kelvin. Let's use this, and this is the efficiency, the maximum efficiency in terms of the 2 temperatures. So let's use this result in application of this problem here, 2019, which says you design an engine that takes this much heat at this temperature in each cycle and rejects heat at this temperature. So what are we given? Given QH, we'll just write down what we're given. That's hot, 1.7, 10 to the 4. The temperature, hot temperature, 640, and the cold, the temperature at which the heat is discarded. All right, that's that. And the engine completes 240 cycles in 1 minute, so that's like a frequency. Frequency will be 240 per minute, so we want the frequency to be in cycles per second, so divided by 60, suppose, right? What else? What is the theoretical maximum power output of your engine? And you know that the power is work, the amount of work done and the amount of time taken to do the work. can write that in terms of the frequency. For that work, I'll just write W, so WF. So F, the power max, will be W max. The maximum work done in that amount of time, given by the frequency. All right, and so the maximum work will be done by the engine, by the most efficient engine. So for work max, really must do better on that one. For work max, the work max gives the maximum efficiency, or the E maximum efficiency. That's the efficiency of a heat engine. That will be equal to work max over the amount of heat coming in. In general, for the Carnot engine, the most efficient one, 1 minus TC TH. So for that work we get, and I'll just call it W now, QH, do this algebra, 1 minus TC TH, and solve for the maximum power. So to put all of that in right here, P max, and that will just be power from now on. FQH 1 minus TC over TH. Now these are in MKS units, so this power will be in watts. They want it in horsepower for whatever reason, so we will change the watts from watts to horsepower. So this many watts, and then I've looked this up. There's 746 watts, 1 horsepower. And now that's everything. Let's put in the numbers we have. For F, that's 240 over 60. Q, that's 1.7 10 to the 4. Okay. And everything else, 1 minus 346, 40. 1 over 746. That many horsepower. Ready for Google Calculator, and that becomes 42.7 horsepower. Should be it. Right.